Hopefully at this point we're feeling pretty confident about evaluating limits using the graphs of functions. So now we're going to turn our attention to evaluating limits using algebra. But before we do that, we should set up some properties of limits, sort of some ground rules of limits so that we know how the limit behaves. And luckily for us, the limit has a lot of really nice properties. It sort of behaves the way you would expect it or the way that you would want it to. So this is really nice for us. So we're going to have f and g be two functions, and we're just saying that the limit as x approaches c of f of x is equal to L, and limit as x approaches c of g of x is equal to m, where L and m are two real numbers. Maybe they're the same, maybe they're not. So first up, we've got the limit as x approaches c of k equals k for any constant k. So maybe we look at a quick example here. If I were to look at, say, the limit as x approaches -1 of 3, so this number right here that you're taking the limit of has to be a constant, which means it is not written in terms of x. It is just some number. It can be a fraction, it can be a decimal, it could be a negative number, it could be 0, but there is no x or power of x there. So here, this is going to equal that same exact constant right here. So since it doesn't depend on x in any way, it's just 3. And if you have trouble understanding that, think about what the graph of, because really what we're looking at here, this function right here, is really y equals 3. So let's think about what that function looks like here for just a moment. Y equals 3. So 1, 2, 3. Y equals 3 is a horizontal line at y equals 3. And then I'm approaching x equals -1. So let me get a different color. And as I approach -1 from either side, it looks like I'm approaching this point right here. And that point has a y value of 3. That's why I have that limit. So it's pretty easy to think about what the graph of that looks like and then use that as sort of evidence to back up your answer here. Similarly, for the second property, here I have the limit as x approaches c of x is equal to c. So you can sort of think here about taking this c and we're almost just like plugging that in for x, and so that is our limit. Again, you can also draw the graph of y equals x, because what we're really looking at is, what's this guy? This is y equals x. So if I wanted to graph y equals x, it's a line with a slope of 1, y-intercept of 0. And let's say I wanted to look at, we'll go over here just because we're running out of room, limit as x approaches 2 of x. So let's say right here, 1, 2. So I want to know what is the y value that I'm approaching. So as I approach x equals 2, which is right here, from both sides, from the left-hand side and from the right-hand side, looks like I'm approaching this point right here. Well, that point has a y value of 2, because this is y equals x. So if I have an x value of 2, that means I also have a y value of 2. So this means that my limit must be equal to 2. So here's a pretty simple example. We're going to look at more complicated examples and how we can talk about some shortcuts to deal with those more complicated examples. But for now, again, we're just setting up some ground rules that will help us better understand those shortcuts when we get to them. Let's talk about the third property here. This one says limit as x approaches c of f of x plus or minus g of x is equal to the limit of f of x plus or minus the limit of g of x equals L plus or minus m. And essentially what we're doing right here, actually let me change my color. If you want to think about it this way, for lack of a better word, we're sort of taking this limit and we're distributing it over addition or subtraction. So we're just taking the limit of the first term plus or minus the limit of the second term. So I'm just kind of taking that limit and distributing that over my addition or subtraction sign, which is really nice. Fourth property here, I have another constant k here. It says the limit of k times f of x equals k times the limit of f of x. So here I'm going to take this k. Really what I'm doing, again, for lack of a better word, I'm taking this k and I'm factoring that out to the front of my limit expression. And that's what we have right here. So that if you have a constant multiple, so if you have a multiple of 10 or negative 1/2 or 0, well, 0 wouldn't make any sense here, but you get the idea, hopefully. 7, 8, 9, 10, you know, pick whatever number you want. You can factor that out. You can just look at the limit of the expression that's in terms of x and then multiply by that constant at the end. So here, to just show a really quick example, if I was looking at, say, the limit as x approaches 4 of, say, negative 7x, I could take this negative 7 right here, because that's a constant multiple, and I could factor that out. I could say negative 7 times the limit as x approaches 4 of x. Well, this is negative 7. Going back to that second property now, I know that this guy right here is just going to be 4, so negative 7 times 4, I've got negative 28. So there we're sort of using two properties, and this would be my limit then. The fifth and sixth property are very similar to that third one here. So for, let me change my color. For property number 5 here, if we have the limit as x approaches c of f of x times g of x, we can sort of take this limit and sort of distribute it over multiplication. So I can just take the limit of each factor separately. So I can look at the limit of f of x times the limit of g of x, and it'll save me a whole bunch of time. Similarly, property number 6 here, if I have a rational function or I'm dividing two functions here, I can take the limit of the numerator and the limit of the denominator. So I can just take that limit and apply it to the top part of my fraction and the bottom part of my fraction, provided that the limit as x approaches c of g of x is not equal to 0. So if your denominator approaches 0, then we're going to have a little bit of an issue. And we'll talk a little bit more about that towards the end of this section and in the next one as well. But as long as you have a non-zero denominator, you're going to be fine here. This last one here is a little bit different, so maybe we'll talk just a little bit more about it. It says the limit as x approaches c. Here I have the nth root of f of x equals the nth root of limit as x approaches c of f of x, or the nth root of L. So really what we're going to do here is take this limit and sort of carry that limit statement inside of my radical. So rather than applying the radical first, here what I'm going to do is actually apply the limit first and then apply the radical. This part right here says, you know what, hey, if you have an even n, so if I have a square root or a fourth root or a sixth root, this really only applies for positive numbers. And that's just so that we only end up dealing with real numbers. We don't want to have to worry about imaginary or complex numbers in this class, so we're not going to worry about those. This also applies for powers of x as well. So if you had, say, limits as x approaches c of f of x to the nth power, you can take this limit statement, so I can take this limit statement and carry it into the inside of that power. So I can say this is really all to the nth power, the limit as x approaches c of f of x. So I can evaluate the limit first and then apply the power. So all of these properties put together make our lives much, much easier. The limit's really nice. It has a lot of really nice properties. It behaves exactly the way you would want it to. Now, this is not always the case for everything we talk about in calculus. When we start talking about the derivative, then some of these properties aren't going to hold for the derivative, and we're going to have to find workarounds or other special rules to deal with them. So the limit for right now, really nice way to start this class off. So let's look at some examples here. So here I have the limit as x approaches 2 of f of x equals 3, and the limit as x approaches 2 of g of x is equal to negative 4. Now notice I don't actually know what f of x or g of x even look like. I just know the value of the limit at 2. That's the only thing I know. So everything else I have to do has to rely on those limit properties that we just talked about on the last page. So here in part A, for example, if I have the limit as x approaches 2 of f of x minus 2, here I can take this limit statement and apply it over this subtraction, or distribute it over the subtraction. So I can really say, let's look at limit as x approaches 2 of f of x minus limit as x approaches 2 of 2. And now I can say, you know what, hey, limit as x approaches 2 of f of x, that's really equal to 3. So I can take out this yellow highlighted part and replace it with just 3, because I know exactly what that is. I have that equation. I have that equality. Minus, over here we're going to have to do use a different property, but notice that this guy right here, 2, is just a constant. So that means it's not going to depend on what value x is approaching. Now it might be a little bit confusing because my constant is 2 and x is approaching 2, but because this constant right here is 2, it doesn't depend on x in any way. This limit will just be 2. And then once I've evaluated my limits, I just have a little bit of arithmetic to do here. 3 minus 2, this gives me 1. So there is my limit. Part B, I have limit as x approaches 2 of 7 times g of x minus f of x. Again, I'm going to start this problem off by taking this limit statement and distributing it over my subtraction here. So limit as x approaches 2 of 7 times g of x minus limit as x approaches 2 of f of x here. Now, this piece right here, I could go ahead and evaluate right now, no problem. But the first term, I do have a little bit more work to do with this guy right here. So I'm going to hold off. I like to evaluate all of my limits at the same time, just so that I don't get confused. So I'm going to hold off on that. I'm going to first of all take this constant multiple of 7, and I'm going to factor that out. So I'm going to factor that to the front of my limit. So I'll have 7 times the limit as x approaches 2 of g of x minus limit as x approaches 2 of f of x. And now I can go ahead and I can say, all right, limit as x approaches 2 of g of x. What is this guy? Let me do that in red. So limit as x approaches 2 of g of x. This piece right here is really equal to negative 4. So I can take out that limit statement and replace it with negative 4. So let's do that. Over here I really have 7 times negative 4 minus, hey, limit as x approaches 2 of f of x. We said up here that's really equal to, that's really equal to 3. So I can take that piece out and replace it with 3. And then after that, we just have to crunch a few numbers here. So here I've got negative 28 minus 3 gives me a limit of negative 31. Finally, C, again, we're just kind of taking these limit properties and applying them here. So here I've got some division happening. So I'm going to take this limit and I'm going to apply it to my numerator and I'm going to apply it to my denominator here. So let's see, I will have limit as x approaches 2 of 1 minus f of x divided by limit as x approaches 2 radical opposite g of x here. So in my numerator, I'm going to go ahead, I'm going to take this limit, I'm going to distribute it over the subtraction just like we've been doing. Here in the denominator, I'm going to take this limit and I'm going to carry that into my radical. Remember that last property said, you know what, you can take a limit, you can carry it inside of a radical. So if I do that, my numerator looks like limit as x approaches 2 of 1 minus limit as x approaches 2 of f of x divided by square root. I have limit as x approaches 2 of opposite g of x here. And I'm going to save myself a step of work here, mostly just because I'm feeling a little bit lazy. I'm going to take this minus sign, right? This minus sign here is really just a multiple. It's really just a multiple of -1. So -1 times g of x. Well, -1, I know that that's just a constant multiple. So I know that I can just take that and I can factor that to the front. I can say -1 times the limit as x approaches 2 of g of x. And now this limit's ready to go. I can go ahead and evaluate this. So let's see, my numerator, limit as x approaches 2 of 1, that's just a constant, so it just stays at 1 regardless, minus the limit as x approaches 2 of f of x, and we've said that is 3. Is that right? Let me just double check. Yes. And then in my denominator, I have square root opposite negative, or let's say -1 times limit as x approaches 2 of g of x. G of x is -4, so I have -4 right here. 1 minus 3, -2 over square root -1 times -4, +4. -2 over radical 2. Over 2, right? Square root of 2 is 4. Which gives me -1 as my limit. So, holy moly. That is a lot of math. Now, for some of these, if you would like to skip a few steps and just show, hey, I can, apply my limit properties to get to this point right here, I'm okay with that. But I want to draw this process out as much as we possibly can just so that we can see exactly what the limit is doing, because that's going to allow us to better understand the shortcut that I'm going to show you how to use in the next video.